Studio project is developing pedagogy, hardware, and software which enable and encourage students in the hands-on exploration of engineering principles, devices, and systems that have historically been restricted to specific laboratory facilities. With the increasing complexity of modern systems design, students will benefit enormously from a greater intuitive sense of science, math, engineering, and technology. Mobile Studio provides the opportunity to instantly draw connections between theoretical assumptions and experimental results, without the concerns of laboratory access and equipment availability. The Mobile Studio I/O board was designed to be a low-cost circuit measurement workstation. It includes features such as an oscilloscope, a function generator, digital I/O and pulse width modulation channels, a low-voltage DC power supply, and a high-speed USB interface. To date, these tools have been used predominantly in electrical, computer, and systems engineering courses to strengthen the students' understanding of fundamental concepts in electronic design. The Wireless Expansion Project seeks to push the boundaries of Mobile Studio's Every Day is Experiment Day philosophy by providing students in other scientific disciplines with the same dynamic and hands-on approach to learning. The Wireless Expansion team is currently working in conjunction with the RPI Physics Department to develop a system for the real-time measurement and analysis of physical objects in motion. The Physics Department wishes to use their current sensors with the Mobile Studio desktop to measure range, acceleration, and force in various classroom experiments. The latest version of the base Mobile Studio I/O board, known as the Red 2 board, is outfitted with a Cypress wireless transceiver that uses a printed antenna to communicate on the 2.4 GHz ISM band. A wireless daughter card and separate sensor board were developed to accommodate the requests of the Physics Department. The daughter card contains all of the intelligence and capabilities needed to communicate with the Red 2 I/O board. The sensor board, which connects to the daughter card via two simple socket connectors, contains the hardware for acquiring data from the existing physics sensors. In addition, the two boards are quite small, each with dimensions of less than 2 by 2 inches, and the height of the entire wireless device is only 1/2 of an inch tall when the two boards are connected together. While the Red 2 I/O board is powered by the student's laptop, the daughter card and sensor board are powered by a 3.7-volt rechargeable lithium-ion iPod Nano battery. Here is an example of a simple experiment where Physics 1 students use the Mobile Studio wireless technology to measure the acceleration of a cart on a U-shaped ramp. First, the student must sync the wireless daughter card and sensor, in this case the accelerometer, with the Red 2 I/O board. This is done by a proximity pairing system. Since multiple wireless sensors will be used in the same classroom at the same time, each device must operate on its own frequency. Once brought within 3 inches of the Red 2 board, the wireless card scans for available frequencies and selects a channel on which to establish communication. Now all that is left for the student to do is to set the cart in motion. The Mobile Studio desktop software displays the cart's acceleration in real time right on the student's laptop screen. This actively demonstrates the specific relationship between the cart's motion and variations in the acceleration data. Furthermore, students can save and analyze the collected data to obtain equations for the cart's velocity and position, giving them a more intuitive understanding of the entire physical system. Here is an example of another common Physics 1 experiment where students use the wireless accelerometer and a pendulum to calculate the acceleration due to gravity. It is typically difficult to calculate an accurate value for gravitational acceleration since wired sensors inhibit the pendulum's free motion. The wireless sensor enables students to obtain highly accurate acceleration data and thus to calculate values consistent with the expected 9.8 meters per second squared as learned in lecture.